Welcome back to The Explainer. Today, we're going to dig into a really cool physics puzzle. It's all about how a blazing hot engine and an ice-cold refrigerator are, well, basically the same thing. Sounds a bit like magic, I know, but trust me, it's all just fantastic thermodynamics.
All right, so here's the challenge we're going to crack together today. We've got this thing called a Carnot engine, and its efficiency is pretty low, just 1/10. Now, we're going to run it backwards as a refrigerator. If we pump 10 joules of work into it, the big question is, how much heat does it actually pull out of the cold part? It might seem a little tricky at first, but I promise, we're going to walk through it and all the pieces will just click right into place.
Okay, so to even start to solve this, we first need to get to know the star of our show, the Carnot engine. Now, this isn't just any old engine you'd find in a car. It's kind of like the gold standard. It's a perfect, theoretical engine that represents the absolute best-case scenario. It sets the speed limit for how efficient any heat engine can possibly be.
And that brings us to a super important idea, thermal efficiency. The easiest way to think about it is like a bang-for-your-buck rating. You put heat in, and you get useful work out, right? Well, efficiency just tells you how good the engine is at making that conversion happen.
The whole process is actually pretty straightforward. An engine grabs some heat from a hot source, like burning fuel. It uses a chunk of that heat to do work, to move pistons and turn wheels. But it can't use all of it. The rest just gets dumped out as waste heat into a colder area. So the efficiency is simply the work you got out divided by the total heat you had to put in to begin with.
So, that's an engine. But here's where things get really interesting. What happens if we just flip the whole script? This is where we go from hot to cold, quite literally.
Posing this one simple question changes everything. Instead of getting work out of a natural flow of heat, what if we put work in to force heat to go where it doesn't want to? This one idea is the secret behind a piece of technology you probably use every single day.
And this table just lays it all out perfectly. A heat engine is simple. Heat naturally flows from hot to cold, and you skim some work off the top. A refrigerator is the total opposite. You use work to force heat to flow from cold to hot, which is totally unnatural. It's basically a heat pump, yanking warmth out of one place and dumping it somewhere else.
Because of this reversal, talking about efficiency for a fridge doesn't really make sense. So instead, we use something called the coefficient of performance, or COP for short. It answers a much more useful question. For every joule of electricity we use, how many joules of heat can we actually move?
So, here's the bottom line. With COP, a bigger number is always better. You want a massive COP. That means your fridge is an absolute champ at keeping things cold without making your electricity meter spin like crazy.
Okay, so we've got engine efficiency over here and refrigerator performance over there. They seem like they're from totally different planets, right? Well, it turns out they're actually two sides of the exact same coin, and they're connected by this beautiful, elegant little secret.
And there it is. That formula right there is the key to everything. It's the secret handshake that connects these two worlds. It tells us that if you know how efficient a Carnot engine is, you can instantly figure out how good it will be as a refrigerator just by plugging in one number. It's that simple. Now, get ready for this because it's going to sound completely backwards. If you look at that formula, a smaller efficiency, a worse engine, actually gives you a bigger and better coefficient of performance. How crazy is that? It means an engine that's kind of lousy at producing work is absolutely fantastic at moving heat when you run it in reverse.
All right, deep breath. We've got our tools, we understand engines, we understand refrigerators, and most importantly, we have the secret formula that connects them. I think we're ready. Let's finally go back and solve that puzzle.
Okay, first, let's just remember what we were given. The problem told us the efficiency of our Carnot engine is 1/10. So it's not a great engine. It only turns about 10% of its heat into useful work.
And the other piece of the puzzle, we're putting 10 joules of work into the system. That's the energy we're paying, so to speak, to make this whole refrigerator thing happen. Now for the fun part. We just grab our secret link formula. We plug in that efficiency of 1/10, so our COP beta is going to be 1 minus 1/10, all divided by 1/10. The top part simplifies to 9/10, which we then divide by 1/10. And boom, that gives us a coefficient of performance of exactly 9.
So we have a COP of 9. Awesome. But what does that number actually mean? Well, let's just go back to the basic definition. The COP is just the heat we pulled from the cold spot, QL,
divided by the work we put in, W.
So if we just do a little bit of quick algebra and shuffle that formula around, we can see that the heat we're looking for, QL, is simply our COP multiplied by the work we did. And hey, we know both of those numbers. We're at the finish line.
All we have to do is plug them in. Our COP is 9, and the work we did was 10 joules. 9 times 10 gives us 90 joules. And that's it. We've got it. The amount of energy this thing sucks out of the cold reservoir is 90 joules.
Okay, so we did the math, we got our number, 90 joules. But let's take a second here. What is this result actually telling us about our machine? What's the real story?
What this means is that our refrigerator is actually, it's amazing. For every little 10 joules of work we put in, we get this huge payoff. We move 90 joules of heat. It's 9 times more effective at moving heat than the energy we're using to power it. That's what that COP of 9 was telling us all along. We paid 10, we got 90. That's a fantastic deal. And this all leaves us with one last kind of mind-bending thought to chew on. We all know that a perfect 100% efficient engine is impossible. The laws of thermodynamics flat out forbid it. So, if a perfect engine is impossible, what does that tell us about the limits of perfect cooling? It's just a fascinating little ripple effect, showing how the same fundamental laws connect the engine in your car to the refrigerator right in your kitchen.